Welcome to day 6. We're going to look at inverse of functions. So a little bit of review. A relation is any set of ordered pairs. That means any x and y value. A function is something special. It's a relation in which every input has exactly one output. We talked about that on the first day of class. So for something to be a function, you have to have no repeated input values or x's. So let's talk about what is an inverse. Well, an inverse of a function is we're going to reflect over the diagonal line y equals x, and when we do that, we are switching x and y values. So let's first draw this diagonal line. So what I've done is draw the diagonal line y equals x, and I'm going to draw the mirror image of these points. I marked some points in gray on the original graph. They're here in gray. I'm going to switch x's and y's. So 0, 0, still 0, 0. It becomes 2.51 when I reflect it, 4.3 comma 3 when I reflect it, and it's back to 5, 5. So 2.5 kind of 1, 4.3 kind of 3, and find this point here, and if I draw the graph, you can kind of see that that blue graph is a good reflection of that original black graph over the diagonal line y equals x. So is the blue graph, is the inverse also a function? Yes. If you recall in Algebra 1 we did something called the vertical line test, where if a vertical line hits a graph in only one point every single time, it is a function, and in this case it does do that. And we'll talk about our notation. F of x is function notation. F with the little raised -1 is the inverse function notation. So don't call it f raised to the -1, it's called an inverse function, or the inverse of a function. So let's talk about how can we tell. We already briefly just talked about the vertical line test. The vertical line test is what we do to determine if an original graph is a function. So when I do a vertical line test and it passes, it is a function. The horizontal line test determines if the function is a one-to-one function. That means there's no repeated inputs or outputs, and that means its inverse would also be a function. So in other words, on this original graph, if I did the, if I do the vertical line test, it passes as a function, and when I do the horizontal line test to the original function, it passes that, so that its inverse would also be a function. And if a function passes the vertical line test and the horizontal line test, it's called a one-to-one function, and it's also called invertible. In other words, its inverse can also be a function. So looking at these graphs, I'm going to pick something very light. Obviously this passes the vertical line test, it's a function, and then I can do the horizontal line test, it passes that. So altogether it passes both the vertical and horizontal line tests, so this is a function whose inverse is also a function. This passes the vertical line test, so we know it's a function. It passes the horizontal line test, it is also a function. So again, we have something that is a function whose inverse is also a function. This passes a vertical line test, so it is a function, but if we look carefully and we do the horizontal line test, it does not pass the horizontal line test, it hits it in 2 spot. This is a function, but its inverse is not a function. And in this last one, if we draw a vertical line, it's not even a function. Okay, so which graph below is not a graph of a function that has an inverse? So all these are functions. All four of these are functions. But the very first one does not pass the horizontal line test, so that would be it. These others all pass the horizontal line test, so not only is it a function, its inverse is also a function. So how do we algebraically find the inverse of a function? So again, we're going to switch x and y values. It always comes down to switching x and y values. So here's my function, f of x equals 3x plus 2. I can rewrite it as y equals 3x plus 2. Then I'm going to do the switch. X equals 3y plus 2. This is the switching part. And now I'm going to solve for y using my algebra steps in solving for y. I'm going to get y by itself by subtracting 2. X minus 2 is equal to 3y divided by 3. And I get x minus 2 over 3 is equal to y. And then I want to use the right notation, so instead of calling it y equals x minus 3 over 2, I'm going to call it f inverse of x is equal to x minus 2 over 3. That would be the proper notation. So it's pretty easy to remember. You've known the inverse of addition and subtraction, the inverse of multiplication and division. How about some other things? What is the inverse of x to n, or x to a power? Well, it's x to the 1 over n, or the nth root. So the inverse of a power is a root, the inverse of a root is a power. And when we have a fractional exponent, this is a power and a root together, and its inverse is the reciprocal of that. Okay, is there any restrictions? Yes, there's one major restriction. And we saw this when we did our domain restrictions. And then we can ever do, we can never take an even root of a negative number. So even roots, x squared, or because the inverse is the square root of x, there's some restriction that's going to go on. We'll talk about that if we come to it. So let's find some inverses. First one won't be too hard. I'm going to start off by saying this is y equals. I'm going to do the switch. X equals 3y cubed minus 8. There's my switch. So now I'm going to do the inverse order of operations. So I should add 8 to both sides. X plus 8, 3y cubed. Now this is where some people get confused. I need to divide by 3 first. So x plus 8 over 3 is equal to y cubed. Now I get rid of it by taking the cube root, or the 1/3 power. I don't care which way you write it. So now I have x plus 8 over 3, the cube root, is equal to y. I should use proper notation. So h inverse of x is equal to the cube root of x plus 8 over 3. Make sure that root is completely over that fraction, not just the numerator. It would be wrong if that root is just over the numerator. Now this next problem is going to be a little bit more difficult. Move over. Oops. This is going to be harder, and I lost my screen. I'm going to have to grab it back. Hopefully we can see this now. But we have to do, this is harder because we have x in the numerator and denominator. So if I can find my recording. Sorry about that. Sometimes it happens when I'm on the tablet form that I lose my cursor or I lose my record. So this is going to be a more difficult problem because I have x in the numerator and denominator, so I'm going to have to do a little bit I have to be more careful with my algebra manipulation. So the first thing I'm going to do is going to switch. So now instead of having y equals, I'm going to have x equals 2y minus 3 over 5y plus 2. That's where I start. That's my switch. Not a big fan of having this fraction, so I'm going to multiply by 5y plus 2 on one side, and when I do to one side, I have to do to the other. So I've done that. I'm going to get a nice cancellation over here, but then I'm going to distribute. Distributive property works both ways. And I get 5xy plus 2x is equal to 2y minus 3. Now I have x's and y's all over the place, so my thing is I'm going to get all y terms on the same side of the equal sign. Okay? So it doesn't matter which way you do it. I'm going to move the y's all to the left. You can move all the y terms to the right. So this 2y goes over here. And everything that doesn't have a y has to be on the opposite side. So I'm going to bring this 2x over here. You could have done it another way. It's up to you. When we do that, we get 5xy minus 2y is equal to negative 2x minus 3 when we see that some things cancel out. Cancel, 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 cancel. Okay, now I have both y terms together on the same side, so I could factor out a y. Y, 5x minus 2. I call it the reverse distributive property, because now it's pretty easy to get this y by itself by dividing out what's in parentheses. And when I do this, I get y equals negative 2x minus 3 over 5x minus 2. And if we want to do the right notation, since this problem was called k of x, k inverse of x is equal to negative 2x minus 3 over 5x minus 2. And there is your inverse of that original function we had for k. Obviously, the original problem was a weird-looking function that had x in the numerator and denominator, and we had the same thing over here. Okay, on that last page, those two examples was finding an inverse. That means I give you an original function and you find its inverse by doing the whole switching of x and y's. Now we're going to prove how we do that. And the big thing about proving is that something very special happens, that when you do a composition, the composition of a function and its inverse will cancel. They always cancel. That's the whole idea. When you think about it. Division and multiplication, inverses, they cancel each other. So what we're going to do by proving it is put one inside the other and show that you get x as a final result. So that's what I mean by prove. Prove is sticking the function in the inverse or the inverse into the function. It doesn't matter which way, as long as you do one way. You don't really have to do it both ways, at least not for me. As long as you show, so in this example, we're going to do f inverse. We're going to take the function, put it into the inverse. That's what it says to do here. So we're going to do f inverse of 3x plus 2, and that's going to be 3x plus 2 minus 2 over 3, and then we see something nice happens. The 2's cancel, and we get 3x over 3. Now the 3's cancel, and we get x. We get exactly what we wanted. We wanted to show that by putting one in the other, things will cancel out, and our composition of the inverse and the function go back to x. Now for this example, we're going to do it the other way, where we're going to take the inverse function and put it in for this x. So this is going to be f of x minus 2 over 3, which is equal to 3, parentheses x minus 2 over 3 plus 2, we see that the 3's cancel. We get x minus 2 plus 2. We see the 2's cancel, and we get x. So we did, this time we put the inverse into the original function, everything canceled, and we did get x. For me, when I ask for you to prove it, you have to do it one way or the other. You do not have to do both. As long as you get x by one way, you would always get x the other way. And finally, we're going to look at tables. Normally, when we did function notation f of x, it really was f of input, that x stood for input, and when we got a result, our y value was the output. So, function notation, inside the parentheses was the x, input, and the result was the output or y. When we do inverse notation, that little -1 part is going to make all the difference, that these switch, that this is really a y value, and I want to find the original x that gives me that. Okay? So when we do p inverse of 5, because this is p inverse, this is the output of the function p. So I found the output of function p. I got to find 5, and p equals 5 right here, and its original x, this is equal to 2. So p inverse of 5 is equal to 2. That's because p of 2 is equal to 5. They kind of go hand in hand. One is the function order, and one is the inverse or reverse order. The next problem, I think we're going to do the same thing. This is the output, so I got to find p equals 3, and I find that result, and this is equal to 4, because p of 4 is equal to 3. The next one is 3. I got to find q equal to 3. Q equals to 3 right here, and the original x is 2. Go again to q. Q inverse of 5. 5 is right here for q, so the original value is x equals 0. And then finally, this last one, it says p inverse of 8. So I have to go to the p row and find 8, and this is undefined because p of x never equals 8. It's not there, so there's no original x to get there. So now we're going to take my p and rewrite it as p inverse as a table. This is because p of x is invertible. In other words, every x has exactly one y value, and every y value has exactly one x value. This is called a one-to-one function. The reason it's one-to-one is because there are no repeated input values, which makes it a function, or repeated output values, which means its inverse is also a function. So all I really do, instead of being xp of x, it's going to be xp inverse of x, and we're going to switch all these x's and y's. So x was 0, 1, 2, 3, 4, 5. That becomes p inverse 0, 1, 2, 3, 4, 5. And the p were these values here in the middle row, and they become the x 0, 1, 5, 2, 3, 4. And if you look carefully, for the very first one, p inverse of 5, if you went to 5, its result would be 2, and that's what we had up here. And then finally what we're going to do, we've done equations, we've done tables, now we're going to do graphs. Again, this notation is special. G inverse of 0 means this is a y value of 0. So right here is y equals 0. And if I go on the G graph, which is the diagonal graph, and I go find 0, it is right here at that x value equals 4. So this basically says when y is 0, what x value am I looking for? In this case it was 4. I'm going to do the same thing over here. Here is y equals 3. I got to find an x for it. So here's y equals 3. I go to the g function and I find x equals 1. And then finally, this is a y value of 4. I go to the f function, was the one with the peak in it. So I go to y equals 4, I hit the f function, and I go down, I find x is equal to 2. Okay, hopefully you understand. Ask questions if you need help.